right, so here's an example of the type of problem you might run into for learning objective 2, which is dealing with RC circuits. The RC circuits that we've worked with, you are either charging the capacitor or discharging the capacitor. In this problem, we're told that we have a resistor connected to the plates of a capacitor with a capacitance of 4.62 microfarads. And it indicates that the capacitor was initially charged. So right away, what I am realizing is that this is a situation where, again, as it states, I only have a resistor and a capacitor, and that means that I am going to discharge my capacitor. This is a RC circuit where the capacitor is being discharged. So I want to remind myself what are the relationships that are applicable to this type of problem. Because I'm discharging my capacitor, my charge is dropping off according to an exponential expression with time, and my current as a function of time is minus Q over RC e to the minus t over RC. And remember that we mentioned earlier when we were looking at charging and discharging capacitors that the idea was that this negative sign is indicating that the direction that the current flows is opposite when you discharge it compared to when it was charging up. Let's see, other things that we might want to kind of take note of. One of the things that this problem is talking about, and we're going to come back to in just a minute, is this idea of a time constant. When we're looking at these expressions, we notice that there's this RC in the exponential exponent that's underneath the t, and that's indicating to us that the RC has the units of time, and we call it the time constant of the circuit because it gives you a sense of how quickly either the capacitor becomes charged or discharged. In this particular problem, just to get a sense of what we're dealing with, the time constant is 850 ohms times the capacitance, which is 4.62, times 10 to the minus 6 farads. And this gives me a time constant of 3.9 times 10 to the minus 3 seconds. All right, so now let's tackle the questions that they're asking. The first question says that when the resistor and capacitor are connected, what is the initial current in the circuit? This is the expression that gives us the initial current because this would also be at t equals 0. And so either way, we should sort of be able to recognize that if we could plug in t equals 0, and we would get the current was equal to minus Q over RC e to the 0, which is this is just equal to 1. And so, or we could just say that we know that coefficient that's out front of the e represents the initial value. Both ways this should work for me. So I have minus 6.9 times 10 to the minus 3 coulombs, because that was the original charge that was on the capacitor. And then RC, you know what, I already did that calculation right up above, so I know that those two things multiplied together give me minus 3.9 times 10 to the minus 3. And so I find that my initial current is 1.76 amps. All right. The next part of this question is asking me to find the charge at t equal to 1 time constant and t equal to 3 time constants. So I'm just going to rewrite this expression for charge as a function of time. And instead of RC, I'm going to write tau, which is our time constant, because this is going to make it a little bit easier for me to do this calculation, because t equals to tau is the first one, and then t equals to 3 tau is the second question that they ask. And so for the first part, I just have my initial charge. So I have, so t equal to tau. I get Q e to the minus tau over tau, and that's Q naught e to the minus 1 equals, my initial charge was 6.9 times 10 to the minus 3 times e to the minus 1. And that gives me a value for Q of 2.54 times 10 to the minus 3 coulombs. Okay, for the next part, I have Q at t equals to 3 tau. So that's going to be 6.9 times 10 to the minus 3 e to minus 3 tau over tau. So it's 6.9 times 10 to the minus 3 times e to the minus 3. So I have to do that calculation. And that gives me 3.4 times 10 to the minus 4 coulombs. So we see that the charge has been largely, has really gone down a lot. And that should make sense because, the amount of time that I'm talking about here is 3 of the time constants. And so that's going to really kind of get the charge down a lot. And then finally, the last part of this is how long does it take till Q goes to half of its original value? So I'm going to use Q of t equals, Q e to the minus t over tau. And so I'm going to say I want this Q to be Q over 2 equals Q e to the minus t over RC. I'm going to divide both sides by Q, and I get 1/2 equals e to the minus t over RC. And I'm going to take the natural log of both sides, and so eventually I'm going to solve for t is equal to minus RC, natural log of 1/2. And I see that that time ends up to be 2.73 times 10 to the minus 3 seconds. And so we see that that time is even a little bit less than the time constant, and that kind of helps us understand how the current decreased so quickly when I was answering my questions to part B. So hopefully that this is a little bit helpful.